Okay, so hey, how are you? So welcome to this another week of our online lectures on multimedia, and this week is the second week. So I believe that all of you have decided to continue this course. The chapter that we'll be starting is multimedia data types and formats. So multimedia data types means that we will be definitely need to study image data representations and formats, audio data representations, video data representations, and all other data types representations that we know. But in these chapters, we'll be primarily focusing on image data types, and the other data types will be coming at the time. Especially the audio data formats is different from image and video. So let's see. It starts with graphics and image is our main target in these chapters. There are so many other popular file formats definitely, and that we'll be seeing those, and we will be also trying to cover some programming practice. So that means how the basic data representations we can understand using programming. And here is a YouTube video. So I recommend that you go in this video and you see why so many image file formats are there. So the image file formats, these are different image file formats here. For example, BMP, DIB, GIF, JPG, and all others, TIFF, WMF, PNT. Also, you see that what are the sound file format. There are definitely MP3, wave, dot wave, and there are others, AIFF, dot AU, and the video file formats AVI, dot MOV, and then you have, color palette file formats also, dot PAL, dot ACT, and then you have animation file format. For example, PPT itself is basically an animation file format, and GIF is basically, it supports both image and as well as the animation file formats. So then FLC, FLA, and DIR, that is Adobe Director. Then in some other formats that here we see. But if you can see that these file formats have been divided into two categories usually. That is, one is for importing and another is for exporting. But then there are another category that we say native file format. Now what are these import and export and native file format? So to understand this, let's explain this one, and in brief, that this is not our target to study. So you see, let's say this is your computer systems, and sometimes what you do from your computer, you basically export some file to other applications. For example, so even it might be through internet, through server, or whatever it is. So the theme is that from your systems, when you export file to other applications, so at that time some file formats are more suitable than some other forms. So that's why we say that some file formats are more suitable for export and some others for import. So definitely import is the very reverse and opposite, that from other systems, if we like to import in our system that we are using, so at the time we said it is an importing operation, and there are some particular file format that are more suitable for importing. So that's why you see these file that we see, these are basically more suitable for file importing, and this file format BMP AVI.mov is for exporting. Definitely there are some file formats they are suitable for both importing and exporting. Now there are other file formats that we basically don't import, don't export, but those file formats are basically utilized and used as suitable for system itself. For example, there are many file formats that we usually see in the Windows operating systems. For example, .exe file, right? Similarly, .dir file, .dxr file. Depending on the systems, you have this kind of file formats. And it is good to note that this GIF and JPG, that is JPEG image, these popular file formats are basically most of the web browsers, they use it, and this is good for compress, decompress, display in many ways for different kind of manipulations. Okay, So there are some abbreviations for some popular file formats. For example, GIF means graphics interchange format, JPEGs mean joint photographic expert group, TIFF mean tagged image file format, and so way. For example, AVI mean audio video interleave, then MPEG mean moving picture expert group, and MP3 is basically MPEG 1 and then MPEG 2 audio layer 3. Yeah, this is a little bit bigger abbreviation. So some of these file formats and some of the things that will be coming across maybe in different times throughout this course. But let's jump in our today's lesson. That is image representations. Now it's better I off my face. So okay. So this is see 1-bit image. Now what do we mean by 1-bit image? Think about, as we know that an image can be considered, for example, this is an image, right? So this image basically you can consider this as a 2 dimensions. So one dimension is maybe, let's say, X dimension, and another dimension, let's say Y dimension. That means row number and column number. So we can think of this kind of 2 dimensions. And then if we consider this 2 dimension, we can consider that this is pixel number 1, this is pixel number 2, this is pixel 3, pixel 4. This is the first line, right? And then similarly you go to the second line. We don't know that how dense the lines are. We are not thinking that right now, but let's think about that the image is basically a 2-dimensional formats. 2-dimensional, that's rows number and line numbers, or rows and columns. Okay, now if we represent the each pixels, let's say we consider that each pixel that in our image, for example, let's say this is a 2-dimensional image, and there we can consider some imaginary pixels, let's imaginary line, okay, and in this way. So this is the thing, and for example, maybe this one is 1 pixel, and this is another pixel, and this is another pixel, right? So, and this pixel, let's say it might be perfectly black or might be perfectly white. So if we just go in this way, let's say, so that means we can basically form a black and white image, or we can also say monochrome image. So exactly this picture is basically a black and white version of this picture. Okay, so in these pictures, if you just choose any pixel, it is completely black or completely white, and still, so just 1 pixels, if we consider black and white, then still we can imagine the photo, right? Imagine the picture. So that kind of image we say monochrome image. Okay, so that means in these cases, to represent 1 pixel, how many bits we require? Definitely we require only 1 bit of information. If we think that if we like to store this entire image in our computer, so that means for each pixels we need 1 bit. For each pixels we need 1 bit of information, and this bit might be 0. If it is 0, so we understand that this is black, and if this is 1, so we understand this is white, right? So if this information is now passed to a computer monitor, so the computer monitor in that particular pixel, it shows either black or white. So that means for each pixel we required 1 bit of information. So this is a very simple things. Now if we consider in this manner, so if we consider in this manner, let's say if an image size is, let's say, 640 by 480, okay, 640 by 480. If this is our image size, if this is an image size, so that means what? The 640, you have 640, let's say, column number, and 480, let's say, row number. So that means this is an image. We can see in this way that how many columns are there. How many columns? Let's say 640 column, okay, this width, or we can say image width. And how many rows are there? Let's say 480 rows. Let's say 480 rows. So that means this one. Okay, so in this way we can consider. So this is an image size. So if this is an image size, so what is the how much storage we need in our computer to store this image, this 640 by 480 image, this image. So definitely you know that how many pixels are there, because there are 640 columns and 480 rows. So that means this number of pixels we have, this number of pixels. And for 1 pixel, how many bit we need? We need 1 bit. So that means 640 multiplied by 480 multiplied by 1. So definitely this number of bits of information, or this number of bits we need to store our image in a computer, okay, or in a computer memory, whatever. So, and then if you just divide this one by 8, so then you can convert these things into a bytes. And then if you so then how many bytes will be there? If you just do the simple math, then it will be coming, this is 400, this number of bytes, okay. Now definitely this 38,400, now if you divide it by this one by 1024, definitely then it will be around 37.5, definitely it will be kilobyte, because if you divide byte by 1024, then it will be kilobyte. Similarly, if you divide bits by 1024, it will be kilobits. So here is a simple a simple mistake. You can see this will be kilobits, not byte. This big B, it means byte, okay. So don't be confused. For example, here you see bits, we first divided by 8, so these will be our bytes, and then if we divide the bytes by 1024, then it will be kilobyte. Now again, if you divide this one by 1024, that would be in megabyte. But we already have this number is small, so we are not doing that, okay. Now let's move. So this is we say this is a 1 bit image. Why 1 bit image? Because for each pixel we assign 1 bit. This is also called binary image. Why it is binary image? Because each pixel either black or white, only 2 options. Now 2 options mean binary. This also called monochrome image. Monochrome image means single color, right? Actually there is no color here, only black and white. It means absence of light or presence of light. So that's why it is also called monochrome image. Now before we move to the next slide, in front of us there is, you see this beautiful color picture. This is a picture of Lena Forsen in 1972. So so this picture, we say Lena image or Lena picture, Lena photo was published in a long back, right? This around 50 years back. So at that time it was published in some sort of magazine, entertainment magazine. And from that time, somehow computer scientists or image processing experts, they use this image as a test image for different kinds of image manipulation, image processing algorithm development, and many other purposes. So it is kind of programming hello world, and similarly in image processing, this kind of image we say hello image, okay. Now we talk about 8-bit gray level image. We had 1 bit, now we are talking about 8-bit gray level image. It is not necessary that each pixels you just say that it is perfectly black or perfectly white. Rather than it is possible that a pixels might be perfectly black, or it might be perfectly white, or it might be somewhere in between. So that means some gray level, okay. So for examples, let's go to the next slide here. You see, so this let's say this one. So how many gray level is possible? Well, it depends on a person or a system design and whatever. But let's say for this time being, we can say that let's say we will consider 256 different gray levels. Now 256 different levels mean what? This is the perfect black, this one, and this is the perfect white, okay. Now in between, you see, as you go rightward, so the black level is reducing and the white is increasing. And as you go the rightward, as you go the downward, and then you go the rightward. So as you go downward direction or rightward direction, the black, degree of blackness is reducing and the whiteness is being increased, right? So these are we say the gray level image. So accordingly, this Lena image, if we consider that, okay, each pixel, even though it's a color pixel, but if you consider that each pixel, which gray level it represent. So maybe let's say gray level, it might be gray level, let's say 0 to 255. So that means 256 different level. If we start from 0, so that means it's ended up with 255. So for example, gray level 127. Now gray level 127 is actually this one. Now if it is gray level 2, or I don't know, maybe 239. So this is gray level 239, and maybe gray level 128. This is gray level 128. So in this way, each pixel, might take any values from 0 to 255. Now 0 means this one and 255 means this one. Okay. So now interestingly, if we convert this way, then Lena image, then this will be our gray level image. Okay. Now think just a little bit more that if it is if this pixel, the gray level is 255. Now if we want to represent this 255, how can we do so? So 255, how can we if 255, let's say 255, and computer they understand all either 0 or 1. So this 255 computer would not understand it, but we will understand. So ultimately we have to convert this to a binary number, right? So in binary number, if you convert, then this will be like 8 1, right? This 4 and this 4. This is the 255 in binary. So and this is exactly the binary number. And so how many bits we need to write this 255 in binary number? So definitely we need 8 bits, right? 8 bits. So if this requires 8 bits, definitely this one also we need 8 bits. Any numbers that we assign, for example, level number 64, and for example, this is black level 0. So if the gray level to represent, to store the information for gray level 0, we need 8 zeros. So that means 8 bits we need to store 1 pixel information, right? Because we don't know that, for example, each pixel randomly, if we choose, let's say this is an image, and randomly if we choose, let's say this pixel, and we don't know that which level it should be, it might be level 127. If it is 127 and we know that what is the binary number, maybe this, it means this one, and then we need to convert to a binary number, and this binary number we require 8 bits. So that's the idea that we say the 8-bit gray level image, and this is the standard gray level image. Okay. Now so that means each pixel we can assign as a gray level, and to represent that gray level we need 8 bit. To store that gray level information, we need 8 bits in computer memories. So that's the idea. Okay. Now think that you remember that the image size that we started with, one image example is 640 by 480 image, right? So this is an image size. Now if this is an image size, and if we have a 8-bit gray level image, so then what is the storage requirement for that? Definitely 640 multiplied by 480, so this number of pixels. Now if we multiply, because each pixels we need 8 bits of information, so that means this number of bits. Okay. Now if we divide this one by 8, so definitely we will convert to a byte. Now if we further divide by 1024, definitely it will be converted to kilobyte. If we further divide it by 1024, then it will be converted to megabyte. So that's the idea. So that means if we like to store a 8-bit gray level image of size 640 by 480, then we need these sorts of information. If we represent in kilobyte, then it would be you can calculate it, and if you just represent in kilobyte, it will be 300 kilobyte, and if you represent to a megabyte, so it will be 0.2929 megabyte, something like that. Okay. Now how about another example that would be give? Let's say our image is size is 1600 by 1200. If this is our image size, then what is the storage requirement? this image mean 8-bit gray level image. So definitely for 8-bit gray level, for each pixel we need 8 bits, and then if we divide by 8 it would be bytes, and if we divide it by 1024 then it would be our kilobyte, and if we divide by 1024 then it would be our megabyte. And accordingly, this would be, if you just do the math, then it will be around this kind of kilobyte, and if you divide again by 1024 then it would be megabyte in 1.831 megabyte. Okay, so I hope this is a very simple math and calculation, so you understand that. Now see, when we are saying that image might be 640 by 480, and another times we might be 1600 by 1200, it depends on our image, that how many pixels we have or what is the image size, so that it depends on that, right? Okay, but then we are using some another terminology. We are saying image resolution. Now image resolution here we are saying that refers to the number of pixels in a digital image, and higher resolution always provides better quality. Okay, so that's correct. But then here we assuming in both cases the image density is basically, we didn't mention that. So ultimately how image resolution and image size is different. Image size usually means that how many pixels you have in width and how many pixels you have in the height. Okay, so this is height and this is width. But image resolution, it means that pixels per inch or per centimeter. Okay, so if you have higher number of pixels per unit distance or per unit or per inch or per centimeter, then you can say that your image resolution is higher. For example, so your image may be 300 dpi, it means 300 dots per inch. And another image, if you have 150 dpi, so that means 150 dots per inch, so definitely this resolution is higher than this resolution. So here I didn't give the definition, but you should note it down that image resolution basically means that number of pixels per unit distance. And here that what we are saying is image size. So definitely image size might be large, but your image resolution might be low, right? It depends on that how many pixels you have. But anyway, it's true that higher resolution always gives better quality. So that means 300 dpi image provides better quality. Okay, so that's good. Now there is another terminology we use, bitmap. Now what is bitmap? So the bitmap is exactly that what we so far discussed, that an image, when you consider that image is basically an array of two-dimensional numbers. So that means each one, you see here, the each point we are considering, this one is basically 1 pixels or 1 bit, right? So this is pixels or bit. So these kinds of graphics or image data we say bitmap. Bitmap means we are considering this each pixels as a bit, each pixels that means collections of pixel, collection of dots, collection of points organized in 2 dimensions. So that's the things of bitmap. So bitmap information mean the raw data that we are considering, the representation of data. So far we just gave the idea of 1 bit image. So this is actually a binary image or a monochrome image or a simple 1 bit image. And we also have 8-bit gray level image. Okay, 8-bit gray level image. So that we understood. But actually it is not necessary that you only have 256 different levels. Depending on your system, depending on your design, you might have maybe 128 different levels. We don't need maybe different levels, 256 different levels. So in that case you just need 7 bits to store every pixel in computer. And you also might have 64 levels, so then 6 bits you require. 32 levels, 5 bits require. For 16 levels, 4 bits require. For 8 levels image, so 3 bits. So that means if we say 3-bit image, what does it mean? It means we are considering an image, a gray level image that have 2 to the power 3. So 2 to the power 3 means 8 different gray levels. So this is what it means. Okay, so similarly 8-bit 8-bit image, what does it mean? It means 2 to the power 8. So that means 256 different levels we can think of, right? So accordingly, so similarly, if we just represent 1 bit of information, what does it mean? 1 bit means 2 to the power 1 means you only have 2 levels, and that is exactly binary image that we saw. Okay, now we'll be explaining a concept called concept of bit planes. This is a very interesting concept. So as we already know, that data on a computer is stored as a string of bits. That means sequence of bits that we just even saw. And interestingly, we can take advantage of this fact to perform various image operations. So this is that, we can think that image is basically a sequence of bits. So let's see how we can take the advantages of that. So we are arguing that an n-bit image can be thought of as a set of n 1-bit bit planes. Now what does it mean? You see, an n-bit image can be thought of as a set of n 1-bit image actually. Now this 1-bit image, okay, so how does it look like? Let's say 3-bit image, right? So 3-bit image means what? We already know that 3-bit image means we have 2 to the power 3, so possibly we have 8 different gray levels. So and we can identify these 8 different gray levels is level 0, level 1, and in this way level level 7, right? Because from 0 to 7, so this means 8 different levels. So level 0 we can represent by 000, and level 1 we can represent by 001, and in this way level 7 we can represent by 111, because this is a 3-bit image, right? So 3-bit image means for each pixels we require 3 bits. So let's say now we consider a 3x3 image. 3x3 image. So that means there are 3 lines and 3 columns. It's a 3 rows, 1 2 3, and 3 column 1 2 3. This is called 3x3 image. Okay, and let's say we are considering 3-bit image. So a pixels might have any values from 0 to 7. Okay, so let's say this pixel value is 0, this one is 1, this one is 2, this is 5 3 7 6 4 1, in this way. Okay, now if we just convert to the binary number of this image for our convenience, so this level 0 means 000, this 1 means 001, this 2 means 010, and accordingly this was 110 and this one is 001. We just convert to binary numbers. Okay, now see, the very interesting fact is, now we will see this image. This is definitely a 3-bit image. Now this 3-bit image, we can 3-bit image can be thought of as a n. So that means if it is 3, so this one is 3. So 3-bit image can be divided into 3 1-bit image. So that's what we mean. So how is that works? For example, let's say so very fast image, how we consider. So this one, okay. So this one, you see, just take the very fast bit. So what is this very fast bit? If we just go from right side to left side, so that means this is the lowest significant bit, okay, least significant bit we say, and this is the MSB, that is most significant bit is this one. So this is how we do always, right? If we have a binary number, let's say 101011, definitely this is the lowest number and this is the highest number. We say MSB and we say this one is LSB. Okay, so this is 0, right? If it is 0, so this is 0. Now see, go to the second one and consider the very first one. The very first one is 1, so this is 1. And now go to this one. So here in this number, the very first one is 0, so this is 0. Now you go in this one. So in this one, the very first one is 1, so this is 1. And then go here, the very first one is 1, then 1. And then you go in this number, so very first one is 1, so similarly this is 1. And now go here, this one, the very first one is 0, so this is 0, and 1 0 0, so this is 0, and let's say this is 1. Okay, so this is how we calculate it. So similarly, you go to the next bit. Now we consider the next bit, the second bit. So second bit is 0, so that means this is 0. And here the second bit is 0, so this is 0. Now here the second bit is 1, so this is 1. In this way you also consider another plane. And then the last one, that means MSB, you just now take the very first one, so that means this one is 0, so this is 0. Similarly, for example, this one is the very this one is 1, so that means this one is 1. Okay, so and how about this one? You see, in this one, so the very last one, that means the leftmost one is 0, so that means this is 0. So we got another plane. So we had 3-bit image. Now 3-bit image, now we have divided into 3-bit image. 1-bit image. How is that? So see now this image. This is only contain either 0 or 1, right? So that means this is basically a binary image. And this is also binary image, because this only contains 0 or 1. This is also binary image. So ultimately, it was a 3-bit gray level image, but now we have converted to 3 different binary images. Now this one binary image, because at a time we are considering 1 bit from this original image, we are considering 1 bit, so that's why we say this is called 1-bit bit planes, because this image basically represent one particular plane, and that is the very first bit plane, and this is the second bit plane, this is the third bit plane, or we can say this is bit plane 0, this is bit plane 1, this is bit plane 2, right? There are 3 1-bit planes, 3 1-bit planes. So we say bit plane 0, bit plane 1, and bit plane 2. So that means this is the first bit plane, this is the second bit plane, and this is the third bit plane. Okay, so this is an original image. We converted to this one, like this one. Okay, so and there are many kinds of utilizations that we can have using these bit plane concepts. For example, the one that we did, we say bit plane slicing, actually, right? So this operation is called bit plane slicing. Now this kind of operations we can use in image compression and various other kinds of analysis to understand. Okay, for example, I can give this one. So in front of us, this is a picture. Let's say this image. Okay, this is basically an 8-bit image. Okay, 8-bit image. Now if we just convert this 8-bit image into 8 1-bit planes. So, and at the time, you see, if we just consider the LSB plane, the LSB plane will be looking like this one, and the second bit plane will be looking like this one, the third, 4th, 5th, 6th, 7th, and this is the MSB plane. Now think about, see carefully, look about the LSB plane and the MSB plane. The MSB plane is more about similar to this one. You see this picture. So when we are interested to see visually significant content, at the time only MSB is enough. Only one plane information is enough. So that means you see higher order bit planes contain the majority of the visually significant data. But if you like to see the very subtle details, very fine details, so we need the very low level, low order bit planes also. So that's why we are saying lower order bit planes contribute to more subtle details in the image. Okay. So similarly, here is a picture, and if we convert, to if we perform the bit plane slicing, then these 8 different planes look like this one. So you see, as I said, this picture, this MSB plane mostly resembles this one. But if you go to the LSB plane, it contains very subtle and fine details. Okay, so there are certain applications that where we focus on these subtle and fine details, but there are some applications that where we actually this is actually enough. So accordingly we use these concepts. Okay, so this is called concept of bit planes. Now we'll explain something on 24-bit color image or an 8-bit color image. Let's say first we talk about 24-bit color image. 24-bit color image. 24-bit color image. So 24-bit color image is very easy. You see how color image forms. We already know that, this image is basically combinations of array of pixels, right? Array of pixels. This is pixel at 1 pixel. Now in gray level image we understand that, but how color image form? Definitely color image, the very fundamental property of color is that if you mixed red plus green plus blue, right, blue, if you just mix these three colors in different amounts, then you can produce any color. So that we say RGB color. Well, we will study some other information about the color models later on, but this very little information is now okay. So that means now what? To present each pixel in color image, we need we need red information, we also need green information, and we also need blue information. Now definitely if we only consider red, for example this one, so which red you mean? The red might be whitish kind of very dark, light red, or maybe very dark red. Which level? So among red you might have 256 different levels. Okay, so that means we are thinking red, but among red there might be 256 different options or different levels of red. Similarly in green we might have 256 different options, and blue we might have 256 different options or levels, right? So now again you see, to represent this to represent a level in red, definitely we need 1 byte information or 8 bits. Okay, for this we need 8 bits. Similarly to identify that which green levels we are talking about, so that also we need 8 bits of information. This is also we need 8 bits of storage, right? So that means what? We need 8 bits to represent red levels, or to to identify red levels, and another 8 bit for green level, another 8 for blue levels. So now we need this 24 bits of information to represent and to identify the color of a pixel, right? So similarly that we try to show here that these pixels, we now need 3 bytes of information. That means one pixel, these pixels is basically underlaying, there are we need 3 bytes of information. This is 1 byte, this is 1 byte, this is 1 byte, this may be red, this is green, and this is for blue information. So now you see it's very simple, the calculations, we can do the simple math. So that means what? For each pixel we need 3 bytes of storage. So and if you see the 256 different possible red, 256 different possible green, and 256 different possible blue, if you just multiply all of this, so you see this more than 16 million possible colors there are. So there are possibly 16 million colors we can generate from this one. Okay, now let's go back to our image size calculations. Let's say we have this image of size 640 by 480, and now this time let's say this is a color image. If this is a color image, so can we calculate that how much storage we require in computer if we like to store this image, the color image? So definitely 64 multiplied by 480, now different. Now you see this number of pixels, right? This number of pixels. So for each pixel we now need 24 bits or 3 bytes. So then that means this number of bits we need. And then if we divide this one by how much? If you divide by 8, so that means this will be your byte. Okay, and now if we divide this one by 1024, this will be your kilobyte, and if you divide this one by further 1024, this would be your megabyte of information. And interestingly, if you find out by kilobyte information, this already calculated, this is actually 900 kilobyte. Now you can see that you can try yourself that if it's really true or not. Okay, so you see this one actually, this is, let's say, a photo or image of some forest fire image. Okay, and definitely this as pixels, as there is a pixel, there is a pixel, there is a pixel. I mean, as you go, there is a pixel as you go down. So this is definitely an array of pixels, this one. Now interestingly, so you have how many, for each pixel you have red part, green part, and blue part, right? So that means for these pixels you have red part, green part, and blue part. Now so in this ways, only if you think that, okay, what is the red part? Okay, let's say we are considering that we are considering the red part. Okay, this is only the red plane. More appropriately is a red plane. Okay, now if this is the red plane, now what is the values of this one? So this value means what? The pixels on the red plane. What is this value? There will be some value, right? So similarly, and go to the next pixel. Let's say this pixel. Now in this pixel, what would be the value for the green? I mean, what would be the value for the red pixels? Maybe this is another value, and this is another value. So in the same way, you have at the same pixels you have green plane, and then similarly you have blue plane. Okay, blue plane. So that means for this first pixel, what is the value of this one? For the green part. And for this pixel, again, what is the value of the very first one? This is a blue plane. So there you have the red plane, green plane, and blue plane. So if we see an image in this way, this is our image, and if we split into three parts, then we can say, you see, this is the red plane, this is the green plane, and this is the blue plane. Okay. Now you might ask, it doesn't look like red. Similarly, it doesn't look like green, and it doesn't look like blue. Well, we will discuss that thing later. But now you know that here we have three plane. One is red plane, one is green plane, another is blue plane. And this red plane is basically a gray level image over red color, and then this one is also a gray level image over green color, and this one is a blue level over blue levels. So this is the thing that we are trying to say. So that means this is an RGB image, and if we just divide into the red plane, green plane, and blue plane, so it will be look like this one. You see, red, green, and blue. So that means using these three components, this is called RGB component image, you can basically you are basically constructing this RGB image. Definitely, we are supplying this information to computer monitor, and then computer monitors generate by using three different LED light. For example, in the monitor, there are certain for each pixels, maybe let's say just we are just giving an example. Perhaps for each pixel on a computer, in the back end there are three LED light. Okay, there are three LED light. One LED light may be red, and another LED light, and LED, we are saying LED light emitting diode, and then another light, and then another light. So in this way. Okay, so then how much red light glow, how much green light glow, how much blue light glows, so that depends on the what is the pixel information, and then you are producing the picture. Well, this is how we understand visually, but in the back end, how image generated, that we say channels. Okay, we basically don't deal with RGB components, rather we deal with RGB channels. Now what does it mean, RGB channels? Think about that. This is, we are saying red component, but this one is, we are saying red channel. This is green components, and we are saying this is green channel. This is called blue component, and this is called blue channel. Okay, now can you see the differences? Differences is basically, you see where this red reflects more, maybe here. So in this particular area, these are more white. Okay, and other places are black. So similarly, where this more green looks like, so there are actually those places are actually more white compared to other places. Where more blue reflects, there's more white. So the idea is that, let's say we have this kind of film, and if we just expose red light onto that, so that means only the white part if it is a white part, so red light will be reflected more. So that means we will be seeing this kind of red component image. So similarly, if you just expose the green light on that, the white part will reflect the green light and other part will absorb that light. So similarly, if this is the one, if you just export the blue light on the blue channel, so that means only this red portion, the whitest portion will reflect most of the blue part, and other component, if it is more black, then it will be less reflections of blue light. So as such, we will see the blue component of image. So when this three light just exposed on the image itself, so that means red, green and blue, so red light, the white reflection from the red channel will produce the red component, green channel will produce the green component, and the blue channel will produce the blue component image. And so we visually see this component, and as such this image. So this is how we see the data, right? So now let's move our next part.